In this JK example, already we have seen this is this side, this is route F logic. Total circuit schematic. Total circuit schematic. The circuit schematic of the JK route F logic. This is D register. This part. This side. Next state. Here present state. This route. H logic buffer. Here X input, block diagram, X vector, combination logic, F logic, combination logic H. Next state, here present state, here register, here Y vector, here clock, here reset. Already we have seen this one also. JK example. Not get, JK input, AND gate, OR gate, here D flip flop, output vector Y, clock, reset, reset, five hundred nanosecond, 1 microsecond, 1.5 microsecond, 2 microsecond, 2.5 microsecond. JK inputs here, clock here, Y output vector. This is Y output vector. Clock 0 1 0 1 0 1 like this. Here 0, here 1, here 0, here 1, 0 like this. JK according to data inputs, output varying, reset continuously when function start initially. It will be under function N, it will be 1 only. Then latches we see D latch block diagram. This is the D latch symbol. D data input, E enable input, preset input, reset input, RST clear. 4 inputs D, E, reset. 1 output Q and plus 1. These 4 inputs. These 4. D latch truth table, symbol D E clear reset Q and plus 1 preset to table D direct enable from here, preset from here, reset from here, Qn plus 1 from here. For these T-latch state equations, there is equations when level clock Qn plus 1 equal to E bar Qn plus EDN. E bar, when will be E bar here, and then Qn, this. Okay. This one here, Qn plus E E E dn E dn. EDN means this one. Both are one. D and E. So this equation we got from truth table. SR latch state equations. Here SR latch state equations symbol S latch set R reset F preset for set, reset for clear. This is output. S value here we will produce R value from here, preset from here, preset bar, reset bar Qn plus 1 level clock equation and level clock Qn plus 1 equal to output. That is output. Okay. S bar R bar Qn here. S bar R bar Qn plus S R bar this is S R bar. Example, in D flip flop, D flip flop, D flip flop, D latch. Here data, here clock, output TFF, DFF, D latch here, output. Here this latch TFF, DFF, latch. Here data input in this TFF. Here input as for clock. Actually this input parallelly connected. Here D flip-flop, then another latch, D latch. Sorry, all are latch only. Sorry. And then T flip-flop. This one D flip-flop. This one D latch. Okay. So here another clock input only here and in the D latch also and in T flip-flop. Okay. Then output T flip-flop output, D flip-flop output, D latch output. Simulation. Simulation 100 nanosecond, 200 nanosecond, 300 nanosecond, 400 nanosecond, 500 nanosecond, 600 nanosecond, 700 nanosecond, 800 nanosecond, 900 nanosecond. Data. This one data. Then clock T flip-flop, D latch. Okay. Then D flip-flop. Here 0 will start, here 1 will start. Here this TFF 0 will start, clock 1 will start, data 0 will start. Okay. In 100 nanosecond, what is happening here? Here 0, here 1, here 0, here 0, here 0. Okay, according to this, in 200 nanosecond and 300 nanosecond and 400 nanosecond, 500 nanosecond, 600 nanosecond, 700 nanosecond, at 800 nanosecond available here like this. Okay. 900 nanosecond available like this. Modular sequential logic. Shift registers. Logic design which manipulates the bit position binary data by shifting it to the left or right. Major application: serial data to parallel data converter. Shift registers, name itself shift is there. So in logic design which manipulates the bit position of binary data by shifting it to the left or right. Okay. Major application: serial data to parallel data converters. Okay. For shift registers. Example: design a 3-bit shift register with the following functions. Design a 3-bit shift register with the following functions: S1, S0, S1,